Welcome back again to our course on fluorescence spectroscopy. Uh, we're going, this is our third lecture on fluorescence polarization immunoassays, and I have to admit, for me, this is the most interesting one because we'll learn about some new topics, maybe even those of you who are familiar with FPIs might pick up some new information. So the new information pops out immediately on the first slides. And I'll have to admit, I didn't know about it. That there's a there's certain animals, camels, llamas, and alpacas, that have a different type of immune system and a different type of antibody. And the difference in the antibody is such that it makes it much more useful for fluorescence polarization immunoassays, and it makes the antibodies more useful for therapeutic things like treating cancer. So what's unique about the antibodies among the camelids, which is what they call these three animals, they have this remarkable and unique antibody. This is the antibody that we've seen for all the mammals that we know of as normal mammals. So it's a pretty big 150 kilodaltons, and the camelids have a very different antibody. And we'll look at this one here. Notice what has happened here. The two FAB units here, there's no two FAB units. They're combined into one. And instead of having three more domains going down, they only have two. And we can skip this one with the yellow here. And then, just like has been done with antibodies since the time of Rodney Porter, you can catalytically clip them and get the isolated, the analog of the FAB units. It's called VHH for some reason, and this contains all of the necessary information to bind the specific antigen. I've made that more explicit on this slide. When we were looking at the normal IgG, it's these two domains together that create a binding site for whatever the antigen is. In the VHH antibodies, which have started to be called nanobodies, all the specificity is localized in this one specific domain, and it's 10 times smaller than the large immunoglobulins, which gives all types of advantages in terms of preparation and growth, etc. The camelid antibodies have really, I mean, they're like God's gift. They're 1/10 the size of normal antibodies. They retain the high affinity and the specificity of the normal FAB fragment. They're excellent for cancer treatment because they're small enough they can cross the blood-brain barrier, so they can even be used to treat brain cancers. They can be used to treat solid tumors. I think I mentioned that here. They have extreme thermal stability, and I haven't seen the primary literature on this, but the reviews on the nanobodies, that they're called, say they can be heated and refolded just like the classic protein refolding experiments that were done years ago over at Hopkins. Let's see. They're so small you can even bind two of them to a same protein if they're different epitopes. They can be easily grown in phage bacteria and yeast, and they're certainly keeping the patent office busy. So this was a remarkable discovery. So here's one of the first places it was used for a direct, non-competitive immunoassay for lactoferrin or human lactoferrin, which is found in many places, including breast milk, sperm, saliva. They are active in an immune response. They activate neutrophils. They have an antiviral activity. And in the newborns, they aid in the selection of favorable microorganisms to populate the intestines. Pretty big protein, 80,000 Daltons or 80 kilodaltons. So this, I reduced the size here, but as you can see, the VHH domain is only 15 kilodaltons. Our target protein is 80 kilodaltons. This would usually be difficult to do because if we were using an FAB unit, for instance, the FAB unit, I can't remember the exact molecular weight at this moment, but it's way bigger. I think it's closer to 50 kilodaltons. It would be, as large as the lactoferrin itself. The assay could be designed so it could be performed in solution without even any pre-separation. So here are the results. They made camelid, they made nanobodies to two different epitopes on the same protein, lactoferrin. You could never do that with immunoglobulins because of the small size. The two different nanobodies had slightly different affinities. You can see the change. The delta P is much larger than we saw in any of the previous immunoassays, in particular the competitive immunoassays. So they're quite ideal proteins. They were also used for making antibodies against the spike protein from the COVID virus. So here's the spike protein, which has a huge molecular weight. The antibodies are directed to this receptor binding domain, which is only around 15 kilodaltons, I believe. And so this is the part where the nanobodies are directed to. And even with that small portion for the receptor binding domain, they could develop two different nanobodies that bind to different parts of the spike protein receptor binding domain, and that these antibodies are said to be neutralizing, meaning they will eliminate the virus, not just like we make antibodies to COVID, but we still retain some COVID in our bodies. The color codes here are just to match how they bind to the immunoassay. So if these were immunoglobulins, this section here would be 10 times as large. It would probably be coming off the page on both sides. So it would be difficult to get two binding sites. Here's the immunoassay results they had for the receptor binding domain. And they were, let's see, I think I got something mixed up there. But in any event, the antibody, the polarizations are always higher with the FAB unit because it's much larger, but you get a much larger change in anisotropy on binding the VHH antibody because it has the opportunity to change its binding to the bigger protein, and it can have a larger change in the rotational correlation time. From all the previous two lectures, we've been talking about two types of immunoassays. I'm simplifying a little bit here, but I'm trying to make a point. We've been talking about competitive immunoassays where we need a small drug analog that rotates fast and slows down when it binds to the antibody. And we were also talking about direct immunoassays where the protein, here the labeled protein is an FAP unit. It's binding to a very large virus. So of course, you can slow down the rotation of this very large protein when it's binding to a virus. So we've talking about these two types, and they're always using the same fluorophores. You might have remember the slide I showed where they're always using a rather selective group of fluorophores. The more difficult assays are when both the antibody and the antigen are large, and so you're not going to have, like the HSA here is not that much smaller than the immunoglobulin, so the changes you get in the rotational rate are not that great, or if you have antibodies against the C-reactive protein, you don't expect a large anisotropy change, because remember, all the FIP assays use 4 nanosecond probes, and here we have a plot of the anisotropy expected from molecular weight. And if you have a 4 nanosecond probe and you're binding a 60 nanosecond rotational correlation time to 150 nanosecond correlation time, there's just not much change in anisotropy to see. Or if you go to larger things like trying to bind an IgG to an IgG, going up to 300 kilodaltons, the anisotropies just don't change that much because you're already close to the maximum amount. I think even though it's normally not stated, what happens as you get to larger and larger proteins, you're really seeing what is the freedom of the probe on the protein, and the effective size effect gets blurred out. But if I say that here, that'll confuse everything. So anyway, we're working up here. How can we get away from this limitation? And this is the other new thing I was going to tell you, is an alternative approach. Let's instead of trying to change the molecular weight of the antibody, let's increase the fluorescence lifetimes. And these are another way you can examine larger antigen-antibody interactions. And these are all called metal ligand complexes. The nickname for this is RuBiPi, and I won't even try to say the full name. And here's a dicarboxy RuBiPi. Many of them have lifetimes in the 400 nanosecond range. Groups are still arguing whether it's really a phosphorescent state or not, but whatever state at the metal ligand charge transfer state it goes to, it decays only slowly. We made this species because we were concerned that this is so symmetrical it wouldn't have much of a polarization, whereas this might have more polarization because the electrons would tend to localize towards the carboxylic acid groups. The transition metal ligand complexes are on the surface wonderful because they can have a wide range of lifetimes. So all the ruthenium ones, well, there's 3 in particular that are used. The ruthenium ones have lifetimes around 350 nanoseconds. The osmium ones have shorter lifetimes, around 20 nanoseconds. And then the rhenium ones have remarkable lifetimes, up to 2.7 microseconds. So there's a wide range of lifetimes, and these have very different emission spectra. This would be the most blue one, this would be a little redder, and this would be even more red. They're really not fully explored yet for biomedical purposes, but they sort of require a different type of equipment because the lifetimes are not convenient for time-correlated single photon counting because you'd have to wait many lifetimes between the pulses. They have excellent photostability, so you can leave them in the room lights for a year. But the limiting factor is the radiative rate is small, so you're never going to get them to be as bright as the normal fluorophores that are used in FPIs. We showed that we could do an immunoassay with these. And first of all, I'll point out that we were correct when the dicarboxylic acid, this is the anisotropy spectrum. Remember that's something that's measured in frozen solution, and that has a peak anisotropy around 0.12 or so. But the dicarboxy went all the way up to 0.25, and that's plenty for polarization purposes. So that turned what normally is a very symmetrical probe into something that has useful polarization. In terms of binding between two large molecules, we brought this up many times, the binding of a anti-HSA to human serum albumin itself. And as you can see, as we put in the anti-serum to the HSA, we get a large change in polarization. If it's a non-specific immunoglobulin, we get no change. And it even works in a competitive format. Not a lot of data points there, but we just didn't do that many. So all I can say is that it does work. Having this larger lifetime is useful for measuring binding between two large molecules. Oh, and this was something we wanted to prove that we could also use the long lifetime rhenium complexes, and they also gave a useful change in anisotropy, actually quite a large change when we bound human serum albumin to anti-human serum albumin. Now, yet another class of molecules that are still being developed for fluorescence polarization assays. These also have long lifetimes on the order of 23 nanoseconds. They're called triangulinium dyes. I always have to think before I say that. Triangulinium dyes, they can have oxygens in this location. The more redshifted ones have nitrogens in this location. And as you can see, the anisotropy, which is this line here, is very high on the red edge of the spectrum. Why the anisotropy? Why these authors measured the anisotropy across the emission spectrum, I'm not sure, but it did turn out that there was some small change there. So in order to make these useful, someone had to make a conjugatable derivative of a triangulinium dye. So this NHS ester was made, and these are the excitation and emission spectra, and across that are the anisotropy spectra. Again, I'm going to pretend that the anisotropies are flat across the emission spectrum because we really don't have many examples where it changes or know why it changes. But the important thing is the anisotropy is always higher for the anti-IgG IgG complex than it is just for the anti-IgG itself. So this proves that you can measure the association of two IgG molecules using these 20 nanosecond triangulinium dyes, and these are much brighter than the ruthenium metal ligand complexes I showed you previously. And this, I think, is a pretty remarkable slide because seen one like this before in these lectures where they showed a temperature dependence. But look at what they're showing the temperature dependence of. They're showing the temperature dependence of the rotational correlation times. So don't mix this up. This is not an anisotropic decay or anything. These are the actual correlation times. And you can see that these are for anti-IgG that was labeled. And these are for the complexes of IgG. And the rotational correlation times are essentially double. And you might remember from one of the previous lectures, I said the correlation times were always proportional to the molecular weight. So these are correlation times which could have never been measured with the 4 nanosecond fluorophores that we're used to using. So that is it for the end of our lectures on fluorescence polarization immunoassays. I hope you found these new developments interesting, and we'll see you at the next lecture. Bye.